Kobo here with us today, speaking on building structures and decarbonization. If you didn't know that's what we're talking about today, you're in for a long hour and a half, but it's going to be really fun. So I'm Caleb Deck. I'll talk about myself here in a few minutes, but I'm going to kind of give us an intro for about 15 minutes on kind of why we're here talking about this situation, and then I'll moderate a Q&A at the end that we'll be having. Special thanks today to the Randall Lewis Center for Sustainability with the national group of ULI. They helped sponsor this event, as well as DeLisi. We're glad to have Dan here speaking on behalf of DeLisi. They helped sponsor lunch as well, so a big thanks to them for that. Here are our 2025 OKC sponsors. You can see those guys there at all our events. We're glad to have all these sponsors supporting ULI in all our events this year. Local events upcoming, we got 3 there. You can see them. You can sign up on the website. You know the usual stuff there. National events, we got Youth Leaders Exchange, and then the spring meeting coming up in May. And if you want to get involved in local membership, there's a QR code. This will all be given to you guys at the end of this presentation, so if there's anything that you see you want later, you can get it. And so it'll come back around. Okay. A little bit about me. My name is Caleb Deck. I am the sustainability lead at FSB here in Oklahoma City. I got an engineering degree from Oklahoma State and then worked at FSB for about 6 years, got a license as a PE in the HVAC side of things and design for a while. And then in 2020, ironically the time of the pandemic, my wife and I and our 2-year-old at the time moved to the University of Cambridge in England, got a master's in engineering for sustainable development there, where I really worked on building renovations and just like how do we engage public culture in sustainability options for buildings, right? In 2023, there was about 2.9% of buildings that got green certifications. So there's like 97% of our buildings out there and building owners who are not actively engaged in this idea of sustainability. So how can we just address not everything, but just some low-hanging fruit there? How can we really get to some differences? So the last 3 years, I've been back at FSB heading up our sustainability efforts internally and externally. That results in, like last year, 17 lead and federal projects with almost $2 billion in construction budget that we've been working on. So a lot of progress in our area, a little bit locally, but mostly nationally. And I just have a passion for talking about sustainability and understanding how can we do better in just a little easy ways. So we're going to talk about that. I'm going to start with a quick recap on climate and decarbonization. Why do we even need to talk about this? Why does this matter? And then we're going to have each of our experts give about 15 minutes on what they're doing with decarbonization and these building structure ideas. We're going to really try and focus on like how does this impact us in Oklahoma City and projects that we're working on right now, today, here. What can we do to make things better? Okay, so issues we're facing. First of all, let's start with the definition of sustainability. I know that's kind of a big topic right now, so just a really broad-ranging idea of how we can kind of agree on this is like the idea of meeting the needs that we have right now while also not compromising future requirements, right? A multi-generational idea of success and long-term building success. We don't need to worry about necessarily a lot of different things. You can see some stats on the left there or right there about carbon emissions and energy, and that is a hot topic. And so what we do want to talk today about is a little bit of this building decarbonization idea and how can we reduce the carbon impact that our buildings are having. We know that it's a big part of the industry. 38% of carbon emissions come from our building industry globally. So we need to just, how can we do better? We don't have to be perfect, but how can we do better in that area? So man-made production of CO2 over time, we're going to look at like, is this really something that matters to people? You can see right down here, James Watt in 1769 created the first steam engine. That was what we would consider kicking off the industrial age. And you can see there's maybe a little trend line that starts to go up as far as the gigatons of CO2 emitted per year in the industry. If we take this and then we expand it out a little bit, we can kind of fit this whole graph now. We had to change our y-axis scale, and we have a pretty significant increase going up. If we want to extend this from, that was going from 1900 to 2000. If we just go up to 2019, we go up a little higher, 21, 23, and actually 24 was 41.3, I believe, gigatons of CO2. So not exactly getting better, but we are doing something. If we put this back on our original scale, there we could see James Watt creating an engine. That gets us to 1900. If we want to talk about today's numbers, we need about 11 more charts going up about 45 more feet to talk about that. So it's pretty impactful. But what does this mean for the building industry future, right? Like, how does this impact us now? There's carbon out there, who cares? We've got a lot more people moving to urbanized areas. As they do that, the energy intensity, we know, increases going from rural to urban areas. So we've got this increase in intensity of usage, and also we've got these anticipated growth of gross floor area. In the next 5 years, we're going to essentially globally be building the equivalent of all of North America again. So we've got this urbanization effect, which is increasing our energy intensity, and we've got this massive amount of growth. So if we're going to get to any kind of even like stabilization of the carbon that we're using right now, we're going to have make some big cuts in the way that we design and build buildings to reduce that emissions element. So like if you're trying to get to 2030 buildings being more decarbonized, we need about 35% less than we have right now in like our entire building stock in the US. So a few ways that we'll talk about this today, and we can kind of look at carbon in two ways. We've got operational carbon, so we're running this building right now, there's electricity, there's maybe natural gas-fired heaters in here, running our systems. So that's operational efficiency and operational carbons that are happening right there. You can see on this top left one, as a building extends its life scale, you're getting more and more of those operational carbons because that's taking up more of the time that it uses things. But we also have this embodied carbon concept. So that's our structure, our steel that's here, our concrete and the flooring. Each of those things, as we produce them, as we manufacture them, as we transport them and install them, and at their end of life as well, those all have carbon impacts. So we're going to look mostly today on embodied carbon elements. So why does that matter? Well, here is a pie chart of global CO2 emissions this year. So you got transport, we've got cars there, about 20-ish%. Industry is big, building operations is about 27%, but we got about 23% of our global carbon emissions come from three major factors: concrete, steel, and aluminum. So we're going to talk about how can we eliminate or reduce or improve our production of those things today. There we go, we're stuck. So when we talk about structures, where does this carbon come from? Well, here's our building stock in the U.S. Created each year. We got about 4 billion square feet created each year in the U.S. of construction. You can see actually a really significant portion of that is single-family wood housing, and then you've got also some commercial steel is kind of the second, commercial concrete is third on that list. So this is how much we're actually building, but if we look at the amount of emissions that comes out of that, we really have our huge about 70 to 80% of that comes from the concrete, mostly in commercial and then in residential and residential rehab. So concrete is actually driving a significant amount of our emissions, even though it's really, only a small portion, about 25% of what we're building. It's having about a 75% impact on the emissions that's being produced in our building industry. So what can we do to make this better? We can reuse, reduce, recycle kind of idea. It's pretty simple, pretty straightforward. We've done this all of our lives since elementary school. This is SE 2050. Structural engineers have this idea. If a company signs up for this, they're going to be making an effort to get their building portfolios down to net zero by 2050. So they've created this set of strategies in that these building companies and these structural engineering companies can choose from on how to possibly do that. They're giving them some tracks to develop to make these things better. So we don't need to talk about the 5 bar charts. Those are just different mixes of how to use this. We're really going to talk about those 4 on the right side, the tracks that you can use to sequester, reduce, or improve your embodied emissions in buildings. So we'll talk about design efficiency, electricity, materials production, and offsets. So first thing, I'm going to go through this pretty fast because you're going to hear from the experts on these each really specifically in a little bit. But just really high level, you can buy offsets. Not really the best thing we'd like to do, right? We prefer to make better designs instead of just purchasing wind power in another country. But it's possible. The most important thing you can do is make sure that it's a verified program. There's a lot of shady marketplaces out there selling carbon offsets. I listed a few over here that are really well renowned. And then we're going to look at here really quickly. There's an example, a 10,000 square foot building, which is about the size of a couple of these office spaces that we've got in here. If you were to try to offset those just without doing any remediation or anything else, you're looking at about $2 per ton of carbon emissions, so about $725, which is, I think offsets sound like a big, scary, super expensive thing, but it's not actually maybe as much as you thought it might be. So something to think about, consider if you want to do those things in the future to make your buildings more offset, you can do that, but make sure that they're coming from a reputable source. We can also decarbonize the grid, right? We're getting electricity into this building. That is part of our decarbonization strategy, but also as we're making those materials, as we're making steel and concrete, those things are extremely energy intensive, particularly steel. So the SE 2050 estimates we could reduce about 10% of that emissions from all of our embodied materials if we if we decarbonize our grid. So that's got a whole bunch of other issues. We don't really need to get into that today. That's not in our topic. But there's a possibility of about 10% emissions reduction through decarbonization in the grid. So if we're looking at manufacturing improvements, and that's what Dan's going to get to specifically on some of these later on the concrete side. But steel-wise, we look at about 7% of global emissions from this production. It actually takes about 4 times the energy to make new steel than recycled steel. You can save 72% of your energy usage if you're recycling instead of using new steel. And same thing with aluminum. It's actually about 95% of your energy savings comes if you just recycle that instead of reusing it. And another thing that just like blew my mind when I was doing some research on this is that 70% of steel and 75% of aluminum that has ever been produced is still being used today. Like aluminum is infinitely recyclable, and so every time you throw a can in a recycling bin, that actually gets recycled and reused and made into new aluminum, and it can be infinitely recycled. And so that stuff that has been made centuries ago is still in use today. I thought that was pretty neat. We'll talk about concrete significantly more later with Dan, but basically the big impact here is we could reduce about 15 to 20% of our overall CO2 in the embodied carbon of our building materials if we kind of maybe just alter our building mix designs of the concrete, or if we look at using some substitutions for bits of Portland cement and other things that we're looking at that. So Dan will get into specifics of what DeLisi's doing in Oklahoma City to impact that now. And if we're looking at improvements in wood as well, wood can be really good. Sam's going to talk about this later, but it really matters where it's coming from. The impact of transportation is pretty impactful on this. So we want to make sure that we don't just gloss over the idea that like where this stuff comes from is important. If you're shipping wood from like Seattle to Oklahoma City, probably not the most efficient like carbon-wise thing that you could do as opposed to building locally. And then what we can also do is optimize our designs, right? We get a lot of times, I'll see our structural engineers, and I'm throwing a little bit of shade at them in our industry because I'm a mechanical guy, that they will get a design and they'll say, okay, that looks good. Now, safety factor, I'm going to throw a 30% safety factor on that. And then the contractor maybe looks at it and goes, cool, I'm going to throw a 10% safety factor on that. And then you get these designs that are way overbuilt. They estimate in the SE 2050 you can save 10 to 25% of our carbon emissions just by optimizing our designs, just by using void-filled foundations and other strategically designed materials and foundations in our practices. This is a lot of specific ways you can do design improvements. I'm not even going to get into it because we got a lot of things going on today. You made it through the engineer side of things. Congratulations. We're going to have some fun. And up next is going to be Austin talking about some masonry design. So I'm going to bring up Austin Snell, founder of Building Culture, and he is going, he's going to finish his presentation real quick and save his things up. Just kidding. I promise we all finished it last night because the internet didn't work this morning, so we couldn't update it. And Austin's going to come up and talk about what Building Culture is doing and about some different designs. Come on up, Austin.
I hope to one day know what it's like to have a presentation done a week beforehand like Caleb before I die. Got it. Good now? Really excited to talk to you guys today. I've been playing with this idea of cutting-edge old tech. And what I mean by that is like, we've got so many incredible technologies today, so many incredible materials, but there's also thousands of years of human innovation in construction and architecture and building, and how do you fuse those two for the best possible outcome? So, here we go. Trying to do two things at once. Okay, so Caleb, you actually have probably been here in Cambridge, right? So King's College Chapel in Cambridge. It's the largest fan vault in the world. It's 42 feet wide, which is not necessarily huge, but what's incredible about it is it's 500 years old, it's completely unreinforced stone masonry, and the actual shell of it is 4 inches thick. proportionally, it's the same of an eggshell. Like, think about how efficient that is as a structure, an unreinforced stone shell that's proportionally as thin as an eggshell, which, if any of you know, an egg is actually very strong. Yeah, if you drop it, it's going to break, but if you try to squeeze it at the top, it's very, very strong because of its shape, because of its geometry. And today, we think about ourselves as masters of engineering. We're so smart. We build these amazing bridges. We build skyscrapers. We build all sorts of cool stuff. And we do. We know how to engineer things we didn't know how to engineer 1,000 years ago. And we also have incredible materials. We have industrialization and the ability to produce those materials. And we also have resource abundance, and we have a lot of wealth. But what it's also allowed us to do is to brute force things. We can basically throw a ton of material at something, a ton of money at something, and make it work. And this is just an example of a normal floor system in probably a building like this. We've got unbelievable amounts of steel and concrete just for a floor system. And it reminds me of, too, just on the kind of the more urban design pattern, too. Well, this is actually Newtown, this is Poundbury, but it's more traditional village pattern. And making the point that, this is what we're building here over the right today in the 21st century America is the wealthiest country in the history of the world. And we're building that instead of, this. All the places that we built and loved and visited and spend billions of dollars to go see every year, it's not because we can't do it. We just kind of choose not to. And this also takes a tremendous amount of wealth and waste to be able to even get away with it. People, building 500 years ago couldn't have even imagined wasting as much material and resources we do today. But we're not talking about urban design. So kind of getting back to this idea of cutting edge old tech. I think a lot of people think of tradition as being outdated. But I really think of tradition is proven innovation. It's innovation that's worked over a long period of time. There's a reason that in America, the VC industry it's like the envy of the world, because no one knows what ideas are going to work and what ideas are not going to work. And what's amazing about America is we throw a lot of money at things to see what ideas will work. And 95% of them fail, but those 5% that succeed change the world. So thinking about, how do we kind of continue that tradition and all those stuff, the knowledge that's been passed down, and use that to our advantage today. So setting the stage a little bit, Caleb kind of hinted at this, but we're going to add about 2.1 billion people to the earth in the next 30 years. That's building about one New York City every single month. And that's a tremendous amount. And of course, a lot of that's happening all over the world, in the developed world, and a lot of it's happening in an urban context, where 80% of the buildings are actually concrete and steel buildings. And as you know, how much carbon and just resources the concrete industry and steel industry consumes. And I think to ensure an abundant future, which I really think is possible, I'm not like a climate apocalypse person. I think if we actually adapt and we innovate and we start using our resources more wisely, we can absolutely have an incredible future. And so what I want to talk today about is a little bit these ideas of strength through geometry, funicular form, and material efficiency. Sound very fancy. Funicular form, just to give you an idea, if I had a string, a perfectly flexible string, and I held it taut like this, and I started kind of moving my hands in, and it starts hanging, and I move it in a little more, it starts hanging even more. That's funicular form. It's the flow of forces and how they want to naturally settle. And so holding a chain like that, it's perfectly in tension. So if you flip it upside down, where it's an arch, it's now perfectly in compression. It's a super efficient form. So a normal 10-story building, and I'm using some research from a guy named Philip Bloch out of Zurich. He's an engineer and architect. And a normal 10-story or above building around the world, for the weight of that building, the mass in the building, 75% of it's in the structure, 16% in the finishes, 4% in the cladding, 5% in the imposed load, the people. So basically the building, 3/4 of it, the structure of it exists to hold up the structure of it. Now compare that to a chair. That's 10 pounds, and a 100, 200-pound person can sit in that chair. It's a much more efficient form than the building. And then you look at the floor systems alone in the building. So 3/4 of the building's mass is in the structure. 50% of that, half of that, is in the floor system. So 41% of the mass of a 10-story above building is in the floor in most typical structures today. So an incredible amount of material going into that. Now, I want to teach you just a quick engineering lesson. It'll be fast. So imagine this just being a little brick arch or a concrete arch or something like that. And this red line is you've got forces coming down on it and it's flowing perfectly through it. But then when you get a point load, that line of thrust actually falls outside of the material, meaning that arch is going to fail. But what you can do is you can actually add a little bit more material on top to keep to keep the form in equilibrium, to keep everything within the material. And it's perfectly in compression. And a great example of this is a bridge in Switzerland that was built in 1929. Now, it does have some steel reinforcing in it, but this was an incredible kind of feat at the time. This is a 300-foot long bridge. And look at how just efficient of a structure it is. It's actually very little material. And the guy that designed it, he used graphic statics to really find the form. They call it form finding, where you're actually drawing out all the loads because compression thrust lines want to kind of do this arching form. And so he actually kind of discovered the form of the building itself. Now going back, when you do this, that bridge has a lot of thrust going into those mountain walls, okay? So even if you were to do that in a building or something. Well, if you had a tension tie at the bottom, so imagine just kind of a steel cable or something that kind of cinches it together. Well, now you've got everything kind of circular. It's no longer pushing out. You don't need buttressing on the outside. It's kind of self-contained forces. And if you imagine that as a floor system, a normal rectangular floor system filled with concrete and steel, well, if you actually just design the floor correctly, the way stone concrete, which is an artificial stone, wants to be in compression, if you design it in the way that it wants to be, you can actually get rid of 70% of the material. You can cut out all of that extra concrete and just have this little form that's left. So I want to show you this actually happening in real life. What you were looking at is a floor system from the top down. So underneath, on the bottom side, there's just kind of a light curved concrete structure. There's zero reinforcing in this. It's an inch thick on all the kind of the thin parts, the actual shell of it. And then they are either 3D printing this or casting it. And look at the similarities here to these two things. Pretty remarkable. And so what's really astonishing about this is they're getting rid of 70% of the concrete, 90% of the steel. And they're able to use inferior materials. They're able to use less strong concrete because they're really getting the form right and the geometry right. And that's what I mean by structural geometry. And on a 25-story building, this is pretty shocking. On a 25-story building, 150 by 150, this would save 1,200 concrete trucks and over 12 miles of steel if you were to roll it out. Just kind of amazing how much material you're actually saving. Just to give a little example, they've got 2,600 pounds standing on a 3/4-inch floor plate, and this was made of the material of an equivalent of a cold dark chocolate, as in, like, this is not concrete they're standing on. So they're using an inferior material, they're designing it, paying attention to the geometry, and they're able to do astonishing things. I'm just going to play this video. How do I actually? So this is them installing it on a real building. So this is making it out of research and starting to make it to the real world. And so they were able to prefab this, drop it off on location, and drop it into this high-rise in a matter of, hours. No steel, no reinforcing except for the tension ties on the outside, completely recycled and recyclable, and it's beautiful. So look at, the Pantheon. It's been sitting there for 2,000 years. The diameter is 142 feet, unreinforced concrete. Today, I know there's some engineers in the room. People will be like, this is impossible. You cannot do this. This does not work. We can't engineer it. You're not allowed to do this. It would be totally illegal in so many ways to do today. But yet we have examples from 2,000 years ago of things standing for What are we building today that's still going to be here 2,000 years from now, 500 years from now, 200 years from now? Almost nothing. So I think there's a lot to learn here. La Sagrada Familia in Barcelona, some of Gaudi's best work. You know how he designed it? He hung chains upside down. This funicular form, he was doing form finding. This is actually the model that he made to come up with this design. We think of ourselves as like so smart today because we know math and geometry. And that's great, we do, but there's still all this lost knowledge that we don't have anymore. Some other kind of interesting, I know these aren't buildings, but this is some of the other research going on. Like over here, this is 400 pieces of just cut stone, no mortar, no steel, just all held together in compression. It's incredibly strong. And they're really figuring out how to analyze this stuff computationally with computers so we can actually apply it in the real world to buildings. So I get that we're not going to build a building that looks like this, but they're starting with more complex shapes and then can back into more simple shapes. This is a really thin concrete shell with a carbon fiber reinforcement. I mean, look how thin it is. It's unbelievably thin. And then they're actually using completely reusable formwork, because formwork becomes a really big deal with masonry. And so you want to be able to either reuse it, or it be really, really, really minimal, or even form-free. This is an example of them using kind of the same form-finding principles. They created a load-bearing column out of mycelium, out of mushroom, just to kind of like prove that when you start using materials the way they want to be used, you can do extraordinary things. And this is just a quote that I really like from John Oxendorf. He's a professor at MIT of engineering. Says, at a place like MIT, you could easily fall prey to the idea that we are at the pinnacle of all time, that we are at the height of technological achievement in the history of the world. That's probably true with respect to understanding the human brain, but there are also lost arts. They could do things that we are only beginning to understand and appreciate today. And I really think that's true, and it kind of comes back to this idea of mastery. And I think in some ways it feels like we've gotten a little bit lazy as a society because we do have all this wealth, we do have all these amazing materials, but like I think there needs to be a relentless curiosity about how do we push the ball forward? How do we figure out more? How do we become masters of our craft? And when I think of masters of their craft, they're highly efficient. You know, you're building durable things, you're building beautiful things, you're doing it cost effectively. And construction really hasn't changed that much over the past 100 years. I think there's a tremendous amount of opportunity ahead of us right now. And I want to kind of end with this last guy. It's kind of an inspiration of mine. Rafael Guastavino. He was a Spanish engineer architect, and he emigrated to the US in 1881. And back then, fire was a really big deal. The Chicago fire of 1871 had just burned down 17,000 buildings and displaced 100,000 people. Can you imagine today, 17,000 buildings, 100,000 people displaced? That was, 150 years ago. So he kind of came with this idea of, we're going to build all these thin Catalan vaults, these thin masonry shells, and that's how we kind of solve this fire problem. Well, he shows up in 1881, doesn't speak any English, can't get any jobs, of course, and so he starts building these masonry shells outside, lighting fires underneath them, and then loading them with steel, and just inviting everyone he could get to come see it. Finally, 8 years later, he gets commissioned to do the first public library in the United States, and this is the first ceiling he brings to the public. What's incredible about this, once again, completely unreinforced, this is about 3 to 4 inches of thin clay tiles. By the way, these thin clay tiles, they could be made in mud bricks in Africa or South America, or hard-fired in the United States. There's so many, it's a very, very, very accessible material that could be used all over the world. Okay, look at him start to innovate. Now he's starting to bring decorative elements into this. Once again, these are just, 4 or 5 inches thick. This was at a zoo that he did this amazing dorm. Oh, he's doing all of this without centering. There is no formwork whatsoever. He's placing this with gypsum, fast-setting mortar, and leaving it in place. No formwork whatsoever. It's unbelievably efficient. This is one of the first subway terminals in New York City that he did. And this is one of my favorites. It's a helical staircase at Carnegie Mellon. If you look at just the bottom of this, it's just 3 little layers of brick, and it goes all the way up. And modern engineering cannot prove that this works. In fact, modern engineering shows that this falls down and it doesn't work, and this is not possible to do today. One of the richest things is that it's in the civil engineering building at Carnegie Mellon, which makes me happy. St. John the Divine, largest church in North America, one of the largest in the world, 4th largest in the world. That dome in the middle right there, intersecting the nave and the transect, this was in 1909. They didn't know how to span it because it was 135 feet diameter, 1909. Raphael Jr. proposed a thin shell dome. And they actually went with his idea because it was the cheapest and it was supposed to be temporary. So what's amazing about this is, 1, it's beautiful from the inside. 2, it's still standing 116 years later. It was supposed to be temporary. It's completely unreinforced. It was built without any formwork or centering. And this is utterly astonishing. He did it in 15 weeks. 15 weeks. To give you an idea, the Duomo in Florence, it's a similar size dome, 149 feet versus 135. It took him 16 years. Now, don't get me wrong, that is an architectural feat. I think it's incredible, one of the most, incredible buildings in the 21st century, or not 21st century, in history. But that's actually the evolution of knowledge, of understanding a material enough to be able to reduce the amount of material and be able to do something like that in 15 weeks. I went to Spain a couple years ago to learn how to do this because in my head I'm like, this has got to be really difficult. I went and we built this really quickly and realized this is so easy. And what we're standing on, the little rope around is just basically a little tension tie. It's 1-inch thick tiles. That's it. We're standing on 1 inch of unreinforced, hollow clay masonry. Well, last example, the Oyster Bar in New York City. 3 inches of these thin masonry shells, and it's Vanderbilt halls on top of it. 3 to 4 million people walk over this every single day. These forms are incredibly strong, incredibly durable. And I really think about the importance, Steve Jobs used to put this up, intersection of technology and liberal arts. And I've talked a lot about technology, and sometimes we really get focused on technology or even focused on decarbonization or this idea of sustainability. But really for me, it's about why are we doing it? The intersection of the liberal arts with technology, with how do we serve people with the technology? And I think that there's incredible potential. I mean, we've got computational analysis where they're able to do all these analysis over these amazing designs. We've got material innovation, whether it's geopolymers or concrete that's 40,000 PSI. We've got artificial intelligence, 3D printing, robotics, virtual augmented reality, and I saw a really cool showing of virtual augmented reality with masonry where curved structures are very difficult, right? Like you can't put a string on it. How do you build a curved structure? They were using Apple VR headset, and you can see through it. You can see the brick, and as you're placing it, you can see where you're supposed to place the brick. It like shapes it, and you put it there. Now, granted, that's probably not very comfortable right now, but fast forward 10 years, what's going to be possible with this? But we cannot let go of the idea of like, how do you actually, what is this in services? What is the why? And so I think like fusing that with the humanities, with history and sociology, and what does it mean to be human, and what kind of society are we trying to create? And if we actually are able to fuse those things and fuse the technology with the tradition, I really think the best of tradition, I think that a beautiful and thriving and abundant world is totally possible. And if you want to take a picture of the screen, if you want to know anything else about what I'm talking about, you can go to these guys' website. They're two kind of real pioneers in the industry doing thin masonry shells. And thank you very much.
Hi, I'm Sam Day, and I might be next. Yep. Great. So like Austin, I put my slide deck presentation together yesterday, but unlike Austin, I'm gonna keep doing that because sometimes the current events don't dictate what your presentation should be until the day of, And I'm an architect, small-scale developer in OKC. I chose the topic, actually, of local materials and stuff well before Trump was elected or North American tariffs were on anyone's bingo card for 2025. But now Trump's here, and he's serious about tariffs, but he seems to have a pretty hard time making up his mind if he wants to do it or not. So I thought, maybe us as ULI should start to kind of, think about what our stance is on it and advise them. Is local materials good? Should we penalize things coming from afar or not? Unfortunately, I wasn't really smart enough to come up with a strong opinion in the end, so you'll probably all walk out of here more confused than you came in, but hopefully that's a journey to clarity on local building materials. So in 2012, I was an architecture student at OU, and we did a tour of Devon Tower, and we got the tour from John Picard, the Picard Chilton, and he said, hey, we were looking at this stone here. This maybe isn't bright enough for this, but we're looking at this stone, and he said, this is a sandstone from Zambia. It's the most significant building material selection that I've ever made in my life. And on the drive back, my architecture professor said, well, I don't know if that sounds very sustainable. And that question's kind of always haunted me since, of like, do local materials use less CO2 or not? We know we're supposed to eat, buy local, but some economists and numbers people say, well, it's not that important. I tried to kind of set out to solve this. Has anyone seen The Brutalist? snubbed at the Oscars recently. No, also trying to stay topically relevant, current events. So there's a scene where Adrian Brody is responding to the contractor trying to VE the Carrera marble he specified. And he says, hey, we can get this silicaga marble from Alabama. It's cheaper. It just looks the same. And Adrian Brody pushes back and says, hey, no, it's too white. You know, this is silicaga marble. It's mined Silicaga, Alabama. It is used to build Washington Monument, a lot of the great marble structures in D.C. It's kind of one of the American marbles. And it's so similar to Carrera when they're building the Washington Monument. They made it get certified as being Silicaga before they put it up, just because they didn't want to have Italian marble on the American monument. But Adrian Brody says, no, what I've specified is blue and gray. It's Carrera. This is from the Carrera quarry. Strangely enough, 70-80% of the marble mined here in Carrera, Italy, is actually shipped to the U.S. This is like kind of architects' favorites. Right? We're always specifying Carrera marble, even though it looks pretty similar to the Alabama stuff. So, question is, was it sustainable? Was Adrian Brody, that can't be sustainable, right? We're shipping all this marble from Carrera and we got it in our backyards. It's pretty similar. Well, so it's almost 5 times as far to go from Carrera to Philly than it is from go to Alabama to Philly, which is close to where they're building this in the Brutalist. Okay, so maybe it's less sustainable, but we got to think of how far, how we're getting there. So if we're flying, right, we can take a ton of material about 2,000 kilometers. We're dealing with kilometers because we're talking about global warming, and it's international. We got to be SI. We got to do scientist stuff. So we can go about 2,000 miles from OKC to LA if we're going by plane, using the same amount of gas, more or less, right? We can take about 6 times farther if we go by truck. Using the same amount of gas, we can take it almost 6 times further even still if we go by train. And if we take it by boat, we can take it about 2.5 times further than even the train could. So the efficiency of differences between different modes of travel are enormous, right? Because it's not really distance that we're concerned with as it is the speed of travel, right? The drag coefficient, right? All of these scale linearly, which is coefficient of drag. This is basically aerodynamic shape of traveling, cross-sectional area. The velocity scales exponentially. You ride bikes, you know, right? 15 miles an hour, aerodynamics doesn't matter. 22 miles an hour, it's huge. So the faster we go, the least efficient it is, and it ends up that if you're going by truck, it's more efficient to go from Carrera to Philly than it is from Alabama to Philly. If you're going by rail, Alabama's better. So they're probably using rail then. We're probably using trucks now. Maybe Italians are better. Okay, not the end of the story though, right? So marble's kind of an exception. Most of the building materials we use are composite. They're complicated. There's 7 or 8 things that go into them. So is local, does that mean we could do maybe a less processed material, right? Michael Pollan kind of revolutionized how we think about eating with Omnivore's Dilemma and then Food Rules after that, and kind of tried to push everyone to look at the back of the ingredients list. If it's more than 5 ingredients, maybe we shouldn't be eating it. Maybe there's too many externalities. Maybe there's too many unknowns. It could be unhealthy. Maybe the same could be true for building materials. So this is mapping the energy of different products. This is in Australia because that's the only data I could find. But so stage 0 is sort of the retail stage, right? And then as we move back, we have more and more stages. So this is where it's sold. Whoever sold it wholesale to the retailer, whoever sold it to them, right? And you can see there's a few materials that might be a lot of the energy is consumed in the last process, but most of this material is kind of, the energy is consumed further upstream, right? So you maybe go to Home Depot and buy a panel of zipboard, right? Home Depot doesn't spend that much energy stocking it on the shelf, but somebody had to make the glue. Somebody had to make the waterproofing material. Somebody had to cut down the tree and chop it into mulch and then smash it together and compress it, and that had to be shipped around a billion different times. So if you're not buying local stuff, it's more likely that, there's a lot more steps, it's a lot more complicated, and could be more carbon, more externalities. QMO is kind of the big advocate for this of like, hey, we should be building with monolithic materials, trying to have as few ingredients as possible in building, right? Saying that, hey, back in the day, architects basically got to specify where all their materials came from. The building was made out of 4 materials. It was stone and some metal. And now, if you look at this is from the Empire State Building, but all the material flows that go into it, it's impossible for the architect to really be in control of all of that stuff. So this is a house he built, Colorado. This is just solid, I think it's spruce. It's 4x6 on the sides. This is basically the same construction as a log cabin, just a little bit smaller members. He calls this a stack, 1 material all the way through. In the traditional stick build, we got studs, insulation, zip board, maybe building paper, some cladding, some battens, right? All this stuff. It maybe has a little better R value, but Keel would argue, well, the embodied energy, not that any of these materials in themselves have that, they're mostly wood and cheap stuff, but just the having to truck them through and all these different industrial processes to get all the stuff to the Home Depot on the shelf so you can buy it and go assemble it, ends up being a lot of CO2 compared to just cutting down the tree, processing it, and buying it at the local lumberyard. Even if the R value is worse, you argue, hey, still the energy overall in this process is a lot better to just use the monolithic material. Shout out to Austin, who's been trying to do monolithic building materials for a while. So saying, hey, if we take this back and if we go to monolithic building materials, it puts us as people involved in development, architecture, the building industry, back in control. Back into we can control where the ingredients are coming from because we're only using a few ingredients. Okay, so this is sort of an argument for local materials, or at least less complicated materials there, if not local. Okay, another argument I'd want to make is, well, whether or not we're doing better on the CO2 emissions, do local materials give us better cities? Do they give us stronger economies, right? Do they give us more local control? This is Factory OS in Vallejo. It was, or still kind of is, maybe the biggest pre-manufactured modular housing company in Northern California, right? They were able to, so in big cities, a lot of times we have controls on union labor, and we have prevailing wages, right? Cities like to set regulations for how much the people working in the buildings get paid. Sometimes state governments do that when it's affordable housing that they're subsidizing, right? So part of the way, but they can't really do that for the refrigerators that go into the house, right? For the component parts, for the pre-assembled parts that go into the building, they can't enforce that. They're importing that. That's not built in their jurisdiction. Factory OS is sort of able to subvert this for the entire building process. They say, we can build the entire thing in Vallejo, which is not going to enforce it, and ship it by boat to San Francisco. In the case of Factory OS, they got a deal done with the Carpenters Union in California, right? But it's not all just trim carpenters, it's framers. It's the lowest barrier entry for construction, basically, is the carpentry union. But then they had the Carpenters Union build all of it, the plumbing, the electricity, all of it. And so the plumbers union, the electricians union, the HVAC union, they're all super mad about this. Factory OS says, oh, it's union built. We're going to ship it to and build affordable housing in San Francisco with it. But whether we're for or against any of this stuff, it just kind of says, hey, that it undermines local control sometimes when we're building stuff outside, off-site, and bringing it in. Okay, another issue to consider, because as stuff goes more and more global, we're getting fewer and fewer local jobs when we do construction. More of the stuff is built off-site, More of this stuff is not built in the immediate area. I mean, this is a span of 15 years, and we're looking at half the amount of jobs for every $1 million we spend on construction. Now, inflation should have probably been baked in there too, but I want the most dramatic graph I could get. But if inflation only accounts for about half, a little less than half this effect, right? So it's even worse in middle income countries who are importing steel and glass and all this other fancy stuff that they can't manufacture. And I think it's making us more economically fragile. This is one of Kilmo's books when he describes how the site of the Empire State Building goes from being a farmhouse to a row house to the Waldorf Astoria for 30 years and then the Empire State Building. And then describes all the material flows, like where does all that stuff come from, right? When it's a farmhouse, we're not going very far. Row house, we're intaking materials from a little bit further. Waldorf Astoria, we're getting larger and larger, right? As we go taller, as time goes on, we're bringing in things from further away, right? This is the global map of all of that. So I would argue that's why we're losing jobs for every $1 million we spend on construction in a local area. More of that money's going to other places to buy stuff. This is Thailand, 1997, had a huge boom in the 70s, 80s, and then the Asian crisis, 1997, Bangkok was probably hit the worst. Maybe Indonesia, but really, really bad. Huge real estate bust, huge currency collapse. So I did some research into this, and one thing you really notice is like they start building high-rises as rents go up, and they're importing tons and tons of materials through the late 80s and early 90s, right? It was just steel and glass, but this is the stuff that we make high-rises out of. If you kind of extrapolate, the furthest I could go back was 1988, but let's say it's that. Office rents, were going up and up and up. Not dramatically, but they were going up 13, 15% over a year. They was having 2 really great decades in Thailand. And then, so people want to build more and more and more. And as steel and glass and high-rise technology comes in, all of a sudden they can build 50 stories instead of the 2 stories, right? This is the 2-story traditional Thai shop home, built with 90% local materials. You get a lot of local jobs every time you build one of these. 50-story tower, not built with very many local materials. You don't get a lot of local jobs. But once you can build these, the land is worth a lot more, right? Suddenly land goes crazy because now I can put 1 million square feet here instead of 10,000, right? Huge difference. And it excludes these from being built because the land is too expensive to build this anymore. You have to build the highest, best thing. So we look at land prices jump up exponentially as rents are going up pretty steadily because we've imported the new technology, towers. Imported steel, glass, international construction financing, all of that. And it's made land prices go absolutely crazy. And it's precluded the local stuff. And I would argue that this is made up, but based on our last graph, this is every time you spend $1, fewer and fewer Thai people get employed in construction, right? So when the faucet gets turned off in 1997 with the collapse, instead of those dollars that you spend in construction bouncing around 4 or 5 times in the local economy before they disappear, when you're building with steel, when you're building foreign engineers, foreign money, all this other stuff, the dollars are bouncing around 1 time, 1.5 times before they get spent. So the collapse is much more imminent, right? And so I think there's some, right? Local materials dampen the effects of real estate markets, right? If we're spending with building things with higher multipliers, higher economic multipliers, meaning the dollars are getting spent more and more locally, we're less vulnerable to the booms and busts of real estate. This was OMA proposed the Hyper Tower. This is 1997, Bangkok. Anytime you see an architect propose something like this, collapse is imminent, right? The downturn is totally imminent. Short the stock market. But then the Tower of Babel thing kind of reminded me of that as well. I might not have time for the last part, but this is Bertansky's famous photo. Maybe you all have been here. It's in Philadelphia, and yeah, it's everywhere, right? It's kind of his point with it, but it's like if we have international materials, suddenly everything becomes the same, possibly, and this is just a more boring world versus this is Wichita Falls. Maybe some of you have seen this cannonball architecture. It's stuff that was built out of granite that was found in rivers, so that's why it's like soft, right? It's probably not the ideal aggregate from a concrete perspective, but it makes for a really distinct architecture that only exists in Wichita Falls and kind of south part of, or Wichita Falls, the Wichitas, yeah, the Wichita Mountains. And then I'd also just point out, international building code is something that's also making it a little bit, it's not international. The picture has the globe, but you can see here it's just US and Canada, which is the only countries that use it. But it's also making it kind of hard to do UL testing. All these things we have to think about as architects of like standardization is making it hard for us to use local materials sometimes, right? We only have so many wall assemblies and they have these 12 parts. Like we have to buy that stuff for the rated wall. And that's probably where some of this reform needs to happen. So yeah, that's all I got. Only 1 minute over. Thanks.
Good afternoon. I'm Dan Mayen. I'm quality manager for the Lisi Brothers. I represent the concrete and Portland cement industry. Today I feel a little bit like the bad guy. So what I'm here to do is I would like to present to you what the concrete and cement industry is doing to reduce the carbon footprint in our products, okay? So the other thing is, how can we work together, you as the designers, us as the suppliers, so that we can help and reduce that carbon footprint. So let's start. These are the 4 things that I would like to discuss today, okay? These are some of the key efforts, not the only ones, but key efforts that we're trying to push. The first thing, hopefully everybody here in Oklahoma has heard about Portland limestone cement. Anybody who reviews a submittal for concrete, we've moved to Portland limestone cement, PLC. We're also trying to replace Portland cement with other cementitious materials. We're driving towards performance specifications, and anybody here who has written a specification can definitely help us with that. And lastly, we're also working on the CO2 sequestration on the fresh and hardened states. So let's talk a little bit about all this. Let's start with Portland limestone cement, okay? To understand why concrete and cement are so high on the carbon footprint, let's go back to the way that Portland cement is actually produced. Portland cement is a man-made rock, that comes from natural rocks. Every Portland cement plant that you guys will ever see is located very close to a limestone quarry. If you go to Ada, Oklahoma, that's one of the ones we have, Tulsa, they need that limestone because that represents over 70% of the raw materials for Portland production. What we do is we start cutting back and reducing the sizing of the limestone, okay, into smaller and smaller pieces until we turn it into a raw flour-like material, okay? We add some other components. The acronym that stands in my head is LISA. We add limestone, iron, silica, alumina, LISA, okay? But limestone represents 75% of all those materials. And then we put them into this massive kiln that is probably the size of a football field. If anybody has ever driven next to that Portland cement plant in Ada, Oklahoma, you guys can see those big pipes. They have 2 of those over there. And that's where all the chemical reactions that we need to transform that rock into Portland cement actually happen. After that, what we do is we start crushing it again. There's a very important piece of the process where we quench the material by cooling it down very quickly you know, and that keeps those cementitious properties in the clinker. Clinker is the final product from that kiln. You're going to see it in a second. We mix it with gypsum to control set time, and we ship it to the ready-mix plant or to the sacking facility where we bag it, okay? Now, just so that we're all clear, the Lisi does not manufacture Portland cement. We are a concrete and aggregate producer. We do not have a Portland cement plant. Okay, these are massive investments, and we don't do that. We actually buy the Portland cement from our suppliers, which we are very, very close, and we use the Portland cement in our concrete mixes. Okay? Now, this is the key part where all the magic happens that transforms that raw limestone, iron, silica, and alumina into an actual man-made rock, okay? What it does is it turns all that rock into lava. So the way I see this, we're basically replicating Mother Nature's volcanic activity by taking all that rock, putting it into a very, very hot environment, melting it into lava, and cooling it down very quickly. And that cement clinker is actually the raw material that we then take to turn into Portland cement, okay? So this is just a man-made attempt to reproduce that volcanic activity. If anybody has heard, and we're gonna talk a little bit about it, Romans used to do that pozzolanic material, which is very similar to what we are trying to achieve. Now, if you look at the whole process and you start mapping the carbon footprint of it, most of that carbon is actually coming from that kiln and the preheater before you actually go into the kiln. If you look at it, on the CO2 kilograms per ton, we have about 479 just on the calcination process, which is the reduction of that limestone, CaCO3, into just the CaO with CO2 remaining. So just the calcination process of reducing that limestone into a more usable calcium oxide is turning out to be a very, very CO2 producing effort. The other part that we do, 319 kilograms per ton, is actually the fuel that we use in order to heat up all that material to turn it into a lava. So the Portland Cement Association has a roadmap, and what they're trying to achieve is carbon zero or carbon neutrality by 2050. And they have a roadmap on how to achieve it, and one big thing that is happening right now is that fossil fuel reduction at the Portland Cement plant. If you go to any of the plants here in Oklahoma, they're gonna be using recycled oil, cooking oil from restaurants, oil from auto services, anything that is a very high burning capacity and produces a lot of heat. They use tires as well. They use a lot of debris and actually trash from other industries. From what I've heard, in some European plants, they're actually positive when it comes to the carbon. They don't produce anything based on the fuel because of all the byproducts that they burn. Now, that calcination process, that's inevitable. We cannot do anything. That's the way that the chemistry works in order to produce that calcium oxide and release all that CO2. How do we limit the use of that Portland cement? If you remember when I talked about the clinker being the main product to produce Portland cement, what we're doing nowadays is we're mixing a lot more of that raw flour with that clinker. Normally, the American Society of Testing Materials, ASTM, will allow Portland cement to operate for a type 1-2 at about 5% of raw limestone, okay? What Portland limestone cement is doing is it's pushing that 5% all the way up to 15. Currently, cement plants are actually adding about 10% more. What it's doing is you are optimizing that clinker from the cement manufacturing facility. They're also changing their proportions, different proportions of that limestone, iron, silica, and alumina, so that we don't lose any of the other properties that we need for building with concrete. So we maintain the same workability, finishability, and the same strength just by changing the chemistry of it, okay? And that reduces the carbon footprint all by itself. What we're doing as well is replacing the Portland cement in a cubic yard of concrete. What we do is what we call supplementary cementitious materials. And some of the ones that we use here locally in Oklahoma, the big one is fly ash. Fly ash actually is a byproduct from the thermal plants producing electricity when they use coal. The power plants here in Oklahoma, they're starting to reduce that amount of coal that they burn. So we are having less and less of that fly ash available. The other products that we use, and hopefully you guys have heard about them, is silica fume, which is a byproduct of the chip producing manufacturing industry, slag from steel, and we're going back to natural pozzolans, okay? These are just some of the few materials that we're using. Now, these materials cannot produce strength by themselves. They need Portland cement in order to activate the whole reaction, and then they have a secondary reaction, which is why we call them supplementary cementitious materials, and that secondary reaction produces more of that CSH glue that helps binding everything together. Performance specification. I think this is where we can work hand by hand and help improve this carbon footprint. Caleb was talking about it. We always over-design everything that we do. No different in the concrete industry. I always over-design my concrete mixes, so my 4,000 PSI mix, my 3,500 PSI, per code, they always break above what I need in order to achieve my 4,000 PSI 90% of the times. You know, even in the equations, we calculate the level of low breaks, and we set it at about 10%, okay? So when you are doing your specifications, the idea right now is to move towards more performance instead of prescriptive, so I can use the materials that I know about and use them in the best possible ability to reach the performance that you need in your building, your pavement, or anything you're building or specifying, right? One big thing that I tell everybody is how you can actually start designing per individual structural elements, and you can move that PSI so we don't have to achieve everything with Portland cement. You let those supplementary cementitious materials who have a secondary reaction, let them hydrate so we get the strength at not just 28 but 56 days and 90 days. If you're not going to use that structure at full occupancy for 6 months, you don't need that F prime C in 28 days. We can wait, and concrete can maintain that strength gain for months to come. One big thing that I want to show people is my 4,000 PSI at 28 days uses 20% fly ash, and my GWP, which is the global warming potential, is at about 279 kilograms per CO2. But if you let me go 40% fly ash and allow me to break that same 4,000 PSI at 56 days, now I can add a lot more of the fly ash that we are trying to use and drop the GWT by about 50 kilograms per CO2. So you see how we're starting to have an impact on how much we're releasing on that carbon footprint by playing around with the strengths and the time to get that strength. Okay? I'm getting all these EPDs from what the National Ready-Mix Concrete Association has been producing for a while with their Environmental Protection Declaration benchmarks. What NRMCA does is we actually get together a bunch of producers, we send them our normal mixes, and they will do the calculation on the global warming potential for each combination of straight cement, cement with 20% fly ash, cement with 30% fly ash, 40% fly ash, slag, and a combination of fly ash and slag. So you guys can see how the GWP actually decreases from the maximum all the way down to almost 2/3 or less than what we would have done if we were 100% Portland cement. So finally, the CO2 sequestration that we've been talking about, how does that look? We have two different types of sequestration we do on the CO2 in concrete. The first one is during the fresh state. There are companies out there that have came up with a technology to actually inject the CO2 into concrete. This CO2 will help us reduce about 5% of that Portland cement, therefore reducing that global warming potential. The other thing that we do is during the life cycle of our concrete, we're going to have what we call a sink effect, which the CO2 the concrete surface, just to be exposed for that CO2, is going to start sucking that into the concrete in a phenomenon we call carbonation. Now, if you remember about carbonation, if you took a concrete class, carbonation changes the pH of concrete, so it may corrode the steel in there. What the American Concrete Institute is doing nowadays, they have a non-metallic excellence center so that we can study how we can replace that steel for what we call FRPs. Hopefully some people have heard about that we don't care if we get too much carbonation, FRP is not going to corrode, okay? So, like I mentioned, these are just 4 topics that we're working on, and hopefully they are successful in reducing that carbon footprint. Thank you so much.
All right, y'all thought you were done with me. Not quite. I am not Kara Klosterman. I wish that she would be here today. Unfortunately, she's not been able to make it. This is one of the senior director for the Randall Lewis of Sustainability, the national office in DC. She had a presentation she was going to do on the Better Building Materials report that the ULI national office put together. Unfortunately, she came down sick last week, and so she's not going to be able to be here to share that with us. You can get the report here. I'm not going to go through any of it because we're talking about like 90% of it right now. But you can go on, you can read it. They got some really great topics in there that we're going to highlight, and you'll get this spreadsheet or this slideshow at the end. But in lieu of that, we have, there's her key takeaways, we have Sarah Terry Cobo from the Office of Sustainability here in Oklahoma City, who's graciously stepped in the last minute to save us and give us a 4th speaker. She's going to talk about some permit-ready plans, and we're going to hear what she has to say today.
How am I on time? Oh, I got 12 minutes. Okay, I can do that. All right, I am going to set a timer, though. So.
Last thing, you got note cards on your table. We're going to do Q&A at the end, so if you want to write notes down or questions, you can pick those up here.
Excellent. So y'all are ready for a 4th speaker, right? If we need to all stand up and stretch, that's okay. Sitting for a long time can make us feel a little sleepy. So, my name is Sarah Terry Cobo. I'm with the Office of Sustainability in the Planning Department, City of Oklahoma City, and I'm going to talk about a project that we got started late last year, which is permit-ready resilient home plans. Now, as far as the project is concerned, we received formula funding from the Department of Energy, asterisk. We'll talk about that asterisk later. And it's from the Energy Efficiency Conservation Block Grant Program, EECBG. We love our acronyms, right? And this was $300,000 for the total project. We actually split those funds into 2 different projects. That is for my half of the project. There's other funds available for a different project. And there's quarterly financial performance that we have to do as a result of this federal grant. And fun fact, EECBG funding in 2009 is actually how this office got started. So, okay, why do we need permit-ready resilient home plans? Right? And these are things that we've been talking about this entire afternoon, right? So we know that we need more housing, right? We need more affordable housing, but we need more housing in general, okay? Our energy codes are outdated in Oklahoma City. We have a very high energy burden here in Oklahoma in general, and also in Oklahoma City. We'll talk about what energy burden means. And it's getting hotter due to climate change, right? And then also, of course, as we are very well familiar with, extreme weather is damaging and costly. How many people were up multiple nights this week because of the wind or because of their children or their dogs reacting to the wind? Yeah. Okay. So our energy codes are outdated. This is from our code, residential energy efficiency. And if you can see those tiny words, what it says is residential energy efficiency deleted. See Chapter 11 of the IRC as adopted. And basically what that means is that they struck the energy efficiency chapter. And so effectively we are working on 2009 energy codes. What is your energy burden, right? So your energy burden is, it's just an equation, right? It's the total amount that you spend on your energy bills, and then you divide that by your household income. That's your total energy burden, right? So anything above 6% is considered a high energy burden. It can be, for energy burden can be 3 times as high as what an average household pays for their energy costs. And for some folks, the energy burden is so severe it can be as much as 30%. So they spend 30% of their income on energy. I meant to delete that slide. This is another one talking about energy burden. And climate change, right? It's making it worse. So these fancy calculations are from the South Central Climate Adaptation Science Center. They're located in the National Weather Center down in Norman, Oklahoma. And we work really closely with them to get these climate projections. They're called downscaled, which just basically means they take the national ones and then they scale them to make it locally relevant, right? So this is for us. So basically what this means is it's getting hotter over time. That's the short takeaway. And the other thing is not only is it getting hotter, we are projected to have more extreme heat days by mid-century. So what that really means is that right now we have an average of 9 days over 100 degrees. I genuinely thought it was more. Like, I had to look. No, seriously, I had to go to National Weather Service and like count from last year. I was like, there's had to be way more than 9. No, it was actually 8. There was only 8 last year. And 4 of those were in August. 4 of those days were in August. So why does it feel so hot, right? That's part of what we're talking about here. But the point is, as soon as 2036, we could have as many as a month of days over 100 degrees. And for context, if you know a 6-year-old, 7-year-old child now, that child's going to graduate in 2036. So mid-century could mean 2050. It could mean as soon as 2036. That's really soon. And electricity prices are going to continue to rise, right? And this is a report from Lawrence Berkeley National Lab. Of course, national labs are part of the Department of Energy. This report they came out with in late last year, and basically showing these changes in average prices. And they identified these factors, among others, as reasons why electricity prices are going to continue to rise. And that's in Oklahoma too, right? We need more transmission lines. Regardless of what the fuel source is, we need more lines because our existing lines are aging. And so utility companies are spending more money to upgrade their transmission lines. Utility operation and maintenance spending on their power plants, right? Their power plants are aging, particularly for the utilities in Oklahoma, right? And so they have to spend more and more money on operations and maintenance. All that gets baked into what you pay for your electricity prices. And then also, right, fossil fuels, it's volatile cost. By nature, it's volatile pricing, and that's going to continue to persist. About 10 days ago, late in February, natural gas prices spiked 160%, right? And natural gas prices are relatively low compared to oil and other things, right? But $4.33 1,000 cubic feet, that's huge. Anything really over $2.5, $3 is expensive, just in the grander scheme of things. And so that's going to continue to rise. And then data centers, specifically AI, right? We all know that every time that we use our smartphone, every time we use our computer, every time we do a Google search, right, that takes energy. It takes computing power. There's a data center somewhere, right? AI takes exponentially more power because it's getting all of that, it's crunching that computer power, and it's giving you those answers in, seconds instead of minutes, which nobody can, like really wait for these days. You might remember back in the early days of the internet where you put your AOL disk in and then you sit and then you wait and then, yeah, right? We're all old enough to remember that here, right? So data centers are going to continue to put pressure on electricity prices. Should have put a white background behind this. So electricity prices are rising. Climate change is going to increase the number of disasters that we have, right? Climate-related disasters, weather disasters. So this is for Oklahoma. This is just like in the last 40-ish years, right? You can see that trend line is going up, and you can see where we are having these, 2020, some energy disasters you may remember from there, ice storm. This is my attempt at humor. I'm not great at humor, but Gary McManus, our state climatologist, is. So this comes from the Mesonet ticker. He does some great graphics and brings some humor to weather and climate news. So this is pretty, it speaks a lot, right? Because we had these insane winds. And this is even, so we're looking at high winds and then also tornadoes here, right? 87 miles per hour, that's like an F2 tornado, right? Like that's a lot. And then you can see how many tornadoes that we've had since 1950, right? Many. And then, of course, the larger ones, the larger kind of lines, those are the stronger ones. So we're going to move from, right, it's costly, energy prices are rising, and now we're going to kind of move on to that resilience portion, right, of why we need more resilient homes. So in the Appendix X, the residential tornado provisions from the Oklahoma Uniform Building Code Commission, adopted in 2018, they have this in their index, right? The single most important objective in protecting a structure against high winds is achieving a continuous load path from the roof to the foundation. And I don't know if you can see in the back there, but that is a home, and that is half a home, right? And that was from the 2013 tornado. Connection points. This is the continuous load that we're talking about, making sure the roof connects their roof to the walls, and the floors connect to the walls, and then the walls connect to the foundation. And there are higher standards that are available, that are time-tested, that have been tested in a lab. There's 20 years worth of research. The International Institute for Business, IBHS, I forget the acronym, but IBHS has these fortified standards. This is just one for a roof, for example, but they have ones for whole homes. Basically, it's another certification, yes, but it's also basically proving that you can have a more resilient home. And on their website, they have studies from fortified homes that were built along the Gulf Coast and that have weathered additional hurricanes and windstorms since then. And you can see how much better they performed, how much money they saved. Now, these key terms should be pretty obvious to everybody in this room, right? The way that we can adapt to our changing climate, the way that we can mitigate the damage from, all these storms is in the way that we design and pre-design, right? So obviously pre-design and design is your energy conservation, right? All of these things, your envelope, your natural ventilation, your solar and your shading, your daylight, all of those things. Then once you get to the design phase, right, you're baking in energy efficiency within your HVAC equipment because you've already reduced your energy load here with the efficiency measures. Your internal loads reduction as well. And then on the far right, this is least cost to most cost, of course. Renewable energy, that's kind of, we consider that, as far as permit-ready homes are concerned, we would consider that an add-on if the person has the funds to do it. And this wonderful figure is from AIA's Architect's Primer on Energy Efficiency. So our ultimate goals for permit-ready homes, permit-ready, resilient home plans is, right, we're trying to shield people from rising costs. Not everybody in Oklahoma uses an architect to build their home, unless you're a high-end consumer, right? Most middle-income and low-income folks, if they're buying a house or building a house, it's gonna come from a builder. An architect may or may not be involved. So we want to shield people from those rising energy costs because that energy burden is so high for some folks. For renters in Oklahoma City, for example, it is extremely high. It's about 15%. So if you low-income households who rent, you're paying 15% of your income just for your energy bills. And we want to be able to provide designs to keep those occupants safe, right? We want to keep people in their homes. We don't want to have to disrupt and worry about the latest windstorm on Tuesday that blew your roof off. We want to be able to show energy savings from these more efficient homes, right? The goal is to be able to have an energy modeler that will take these permit-ready designs and be able to show how much reduced energy usage they're expected to have. So we can show an actual savings. Yes, there is, HUD actually has done some research with their new minimum energy standard they released in April, and it was basically for IECC 2021, that it was, you spend, maybe $15,000 more up front, but over the life of your mortgage, you save $25,000. So we want to be able to bring those figures home to a local level. And then also part of our permit-ready resilient homes project is ADUs. We want single-family homes, we want duplexes, we want ADUs. The goal, we are hoping to be able to jumpstart some ADU construction, right? To be able to build more density in the places where it's appropriate. And just to be clear, we want, because many folks have seen different sorts of design competitions and things like that around the country. There's lots of permit-ready plans available for other cities and states, but we want to be clear that permit-ready doesn't mean pre-approved, right? It's as is. The permit staff are going to review it. They know that these plans and maybe your adults are going to they're going to meet this basic criteria. From what we understand, that process is fairly quick to begin with. That's what they say. So it doesn't mean that your permits are going to be issued quicker and it's not automatic approval. The other thing, when it comes to permit-ready homes, we acknowledge that there are a lot of other factors that go into housing availability and affordability and efficiency that we cannot capture with this project alone, right? We cannot control, but we are identifying those things so that we can be able to present them as something that is worth a follow-up, right? And we're talking about financing. We're talking about assessors not including energy efficiency measures within the value of the home or even renewable energy. We've heard anecdotes of folks, having solar panels. They spent $30,000 on a solar system. They moved and they got no effective benefit from that. And then, let's see, financing. Lack of higher energy codes at the state, right? Those are just a few of the issues that we have kind of already identified that we'll be able to just kind of take note of and then address at the, be able to have some sort of follow-up report at the end. Part of our group is, a diverse mix of folks that is even some great folks that are in the room today. So, these are folks who are mechanical engineers, these are architects, these are home builders, these are ULI members that think about urban planning and design, and including our development services folks, and of course, our assistant planning director, Lisa Chronister. So the goal is to get this diverse group of people to be able to figure out how can we do this here in Oklahoma City. Now about that asterisk. If you follow the news, you may have been aware that the federal government has done things with funding. Things have gone back and forth. Our city leadership made a decision that we're going to pause this project and the EV project that the other half of the funding was for, until we get some clarity from Department of Energy on what's happening with this funding, right? There's uncertainty right now, and this is a reimbursement. So it's not fair for us to be able to, spend taxpayer dollars if we don't know for sure the feds are going to reimburse us. And then also, of course, to put RFPs on the street, have, contractors spend time and money on things, and then, us not be able to reimburse. So we are awaiting guidance from DOE. We actually heard from our program officer today. We've got meetings, so cautiously, maybe naively optimistic that we'll have some sort of clarity soon, but that's where it is. So we've got this really cool project that's just kind of hanging out. And that's all I have. Oh, dang. 2 minutes over.
Okay, so you've heard a lot of information today. I hope it was good. I hope it was helpful so far. We're going to have a little bit of time for Q&A. So you've got some note cards there on your table. If you want to write a question down, you can do that. I think Jordan's also going to be running around with a mic. If you have a question, you can raise your hand if you'd rather do that. Our panelists are going to come up here and sit in the chairs. If we do have any note cards, you can go ahead and hand those out now. And we'll get started here just a second. I'm going to give you like 45 seconds to think, if you want to, with quiet, so you can think about questions.
And if you do,
I'll ask you questions.
Okay.
While people are waiting, is there going to interfere with people's thoughts?
while ever,
Maybe. Yeah. Let's give like 10 more seconds.
hello. Oh,
Okay. We do have some primer questions as well, and I know
I have a non-question.
we already got
Hold
Shane,
on.
we got a question here.
I have a non-question. I thought I was just coming here for lunch, and maybe sometime I didn't know I would be topic. So, all four presentations. Oh, thank you guys so much. Keeping me on the edge of my seat. And
Oh, awesome. Thank you. Great question. Hey, good question, Shane. Yes, thank you. Thank you for the praise. So that's great. Sam, did you have a question?
I'll let Mark go first. He hasn't talked. Go ahead.
I was just curious on the concrete portion. I'm sorry I can't say that.
Dan.
When you're mixing materials, that increases the cost currently running purchasers in the cost outside of the efficiencies that are benefit users.
That's a great question. So depending on which material we're talking about, fly ash started, these are all byproducts, but we still do some quality selection of the byproducts. We don't just use any fly ash coming from the power generation plant. We actually classify it. So there is an investment that fly ash companies have to do, okay? Now, the fact that they're local helps because we have a power plant in Red Rock, we have a power plant in Hugo, Oklahoma, so we do get a lot of that material locally. I'm gonna say the cost is about a wash, unless we're talking about using silica fume. Silica fume is very expensive, so then the cost is gonna be higher. We have a product going on with Army Corps of Engineers at the Keystone Dam, where we're using about 5% silica fume, and the cost of that mix is just crazy. But they're trying to achieve 12,000 PSI, you know? So it's also based on what you're trying to do. For a 3,000, 3,500, 4,000 PSI, I'm gonna say it's probably a wash. If you start going higher than that, the cost is going to increase. Great question, thank you.
Dan, what about hydrogen? You know, with the Inflation Reduction Act, there's a lot of talk of blue-green hydrogen as a possible fuel source for these kilns.
Yeah, that's
still
state of the
being
art
talked about, or
edge
not yet?
technology. Yeah, there's actually several startups that what they're trying to do is they're trying to replace all the fossil fuels and even the kiln to produce Portland cement with hydrogen. That's one of the initiatives with solar energy. So trying to melt all that rock and turn it into lava using other alternative sources of heat. Hydrogen is one of those. Solar power is one of those. Right now, it's all experimental. There are attempts to scale it up, but it's not an industrial type of production. But yes, it's happening right now. It just one more way that the industry is trying to reduce that carbon footprint that is, we know that it's really high, so we're doing our best to try to reduce it as much as possible. Yes.
That's great. Sarah, you mentioned earlier the idea of energy efficiency in the building structure itself. It reminded me of one of the projects we worked on. I saw some of the Fitzsimmons guys in here earlier. I think they're gone now. Oh, there, Spencer's right there. When we worked on Phillips Murrah building, and we did some additional work in the energy modeling side to show some value there, and we made some improvements in the glass there. Just thinking of like local examples that we've had, where we increased the glass U values, and I think it was something like a $20,000 add to the building itself to improve the glass efficiency on the walls. We ended up being able to reduce our mechanical loads for 3 of the floors of the building, 10 tons apiece, which is about $30,000 of upfront mechanical savings. It's also pre-tension concrete, post-tension concrete, and so there is structural savings there in both the amount of materials using and the cost of that. There's electrical savings, and then they're ending up running 3 floors of their building at 10 tons cooler all the time rather than more expensive. So they're getting upfront savings and long-term savings. And it took a little bit of extra work. I think we spent a few extra days convincing the owner that this was a good payback there and some energy modeling time. But that energy modeling, that example of showing how our building structures can really prove to be more energy efficient up front and long term, ended up being a really good example for us locally to see, like, what does that really do for us? So that just popped up in my mind. Anybody have any other questions? We got another one for Dan here. That are there any other companies that are following some of the same methods as Delisi? And I think maybe another question is like, how do you see this as a market take up for you guys? Has this been extremely popular somewhat? Is it gaining traction? What does it look like for y'all?
Oh yeah, that's a good question too. We operate only in Oklahoma, and what I can tell you is other states are way ahead of us. We are not at that same level. I mentioned about the environmental protection declarations, the EPDs, and we go to a lot of national meetings, and I have friends in all these other places. So a friend of mine from Kansas, he pulled out his computer, and the way that we produce our submittals is we kind of bind together all the materials we use for concrete, right? Portland cement, MSDS, a MillCert, a fly ash, aggregate, rock, and then at the very back, he had the EPD for that specific mix. And I'm like, how do you know? So they have these contracts with these software companies that they go into their plants and they do a life cycle analysis, and then they assign a carbon footprint to each one of their products per pound. So depending how many pounds of Portland cement you do, you add these many kilograms of CO2, depending on, and they go to each one of those products. So we're not there. We have a benchmark that we participate with the National Ready Mix. I know what my 3,000 PSI does as a benchmark. If I add so much fly ash, if I add so much slag, also if I start cutting back on the amount of Portland, because now we're experimenting with, like I mentioned, silica fume, fly ash. We also have chemical products. I don't know if this is, they're starting to go towards nanotechnology with nanocarbon tubes, and they're starting to do a lot of these experimental things that we are testing to see if we can cut back that Portland cement and reduce the carbon footprint. When I mentioned about the CO2 sequestration, all we're trying to achieve by adding CO2 in the fresh state is 5% Portland cement reduction. And I cannot get it there. At 5%, I'm still struggling to cut back on that one. So for, let's say, 500 pounds per cubic yard, I'm only talking about 25 pounds of Portland cement reduction. Small steps.
Small steps. That's good to know. Both Austin and Sam, you guys are builders, designers, and developers a little bit in your own sense. Can you think of ways that you could help advise those of us who are architects or developers to specifying better materials, or how do we make better selections? How do we encourage pickup of this in Oklahoma City?
I mean, frankly, I don't think about this a lot in my actual practice. It's just, it has to do with sort of building code and UL assemblies and stuff, you know, like, I have a little bit of consternation. I specify brick. The embodied CO2 is higher, but maybe it'll take longer to get demolished or something. I mean, so I don't think about materials themselves the only one I think about actually is spray foam, right? Because it has this big trade-off of like, we get our buildings really airtight really easily, but it has like a ton of greenhouse gas equivalents and possible term formaldehyde toxicity. So there's a huge benefit and kind of huge. So that's the only one I really think have a lot of thinking about in my practice. Actually, I'm really just saying how much denser can I build. But my sustainability thing is how much denser can I build in areas with high walk stores and have shared walls and maybe use extra insulation if I can afford it, or kind of minor stuff really. I'm thinking about it, but not doing it in practice.
I mean, I'm kind of with saying, like, the number one thing, by far, we didn't talk about it today because we're talking about materials. Yeah. We got to build differently, like the recipe. We're talking about the ingredients. Like, there's nothing more that we could do, like, than create more walkable neighborhoods. Yeah. Like, there is just, nothing even touches that. Totally. So, like, until we fix that, and 97% of our city is R1, which is freaking ridiculous. Like, that a few people have decided what the entire city can build and what everyone can do on their property with this tiny sliver. I mean, it's actually an absurd, kind of like an absurdity. And so I think we've got to fix that. And then secondly, like in terms, we're talking about these carbon materials, like I care about the environment a lot. Like generally speaking, I would kind of put decarbonization underneath just the environment and human health. So it's like fixing our walkability and the recipe that we build. And then secondly, I think we need to think about human health and the toxicity of the materials that we use. I care more about that. So when I think about like open cell spray foam, and it's less sometimes about energy efficiency than it is about like all the VOCs and the off-gassing and the bromides and the formaldehydes and how toxic our houses are when they're 5 times indoor air quality can be 5 times worse than outdoor air quality in urban environments. So those two things kind of trump, and then after that, I'm kind of like, all right, now let's talk about energy efficiency. And also I'm like, nuclear energy is probably going to be solved in our lifetime. It should be. And so, I think about durability, resilience, all of those things. And then also, so we care about the materials we use, but it's kind of like Sam, it's hard. And then culturally, I mean, we have to sell things. If someone can build a house for $225 a foot and we're building it for $250 a foot or whatever it is because we use these other materials, a lot of people don't care. And that really matters. And by the way, the banks don't care, They don't appraise it at a higher value. So there's so many things in the way of actually building better. We have to change culturally. We need to change our codes. We need to change our trades, train and stuff. So it's a huge problem. It's not a simple answer to that simple question, but
yeah, that's great. We have one question here that says, wondering about the building material connection to public health outcomes. I think that is a great question. And I think that it falls a little bit outside of our structural idea for the most part, because we do have some emissions coming from our production and manufacturing. I do hope that we can continue this series and do a few more of these seminars over the next 6 and 12 months, where we'll talk about indoor VOC and materials and finishes that happen in that, passive designs and natural ventilation, things like that. So we'll hopefully have some more series that would come and address those more specifically. But we do want to acknowledge that there is a big element to the public health and the materials that we have in our buildings, not just the structure, but the finishes inside as well.
Can I just say on that though, even to Sam's presentation, and we do a lot of masonry, simple, dumb buildings like a triple wide masonry wall or the wood structure he showed, is it the most necessarily energy efficient structure? No, but it's like natural materials, it's dumb tech, there's not all these various ways for it to fail, and I think it does have positive health outcomes, both in the material being manufactured and for the people living in the homes. And so I tend to fall a little bit more on natural building materials when possible.
It's probably safer. I mean,
natural, simpler is better a lot of times.
Yeah. We don't know everything. We've eliminated the asbestos, the lead, the stuff that's really dangerous. Right? We don't build with that stuff anymore. I think there's still a lot of unknowns as well.
What's in a piece of zip board is pretty nasty though.
Yeah, but how much are you breathing in? There's a lot of unknowns still, right? Mm-hmm. With fiberglasses.
Yeah.
How much does it irritate your lungs? Maybe. How much is getting in the air? And especially as we're building tighter and tighter buildings, right? Mm-hmm. We should be more and more concerned with that. It's not that just itself is not a huge concern of mine. I think it's probably, if I had to say underrated or overrated, in my mind, it's probably a little overrated at this point.
Yeah.
If you think about the building materials that are in homes that middle income and low income folks are buying or using or renting or living in, right? We've got formaldehyde, VOCs, and that's, I mean, you go into a new structure and it smells, oh, it's the new home smell, the new car smell, right? That's off-gassing, right? That's your formaldehyde and VOCs, which we know are toxic.
Yeah.
So
Absolutely.
different products, different markets, different scale.
Yeah, still very important. Sarah, we had a question here that despite the funding hold, is there a next step for the permit-ready plans, and is there anything that the ULI community can do to help advance those things?
I love that question. One of the things that we discussed at we've only had one meeting so far, but one of the things that we discussed is there a way that we could do this with, not necessarily private funds, because the city cannot accept private funds, but they can accept donations from nonprofits. The funding that we had, we were looking at 15 to 18 sets of plans, right? So 15 to 18 sets of single-family homes, ADUs, and duplexes, right? And with your energy modeler as well. So we're looking, is there a way that we can scale that down and just do a single set for, like what can we do for 50,000? What can we do for 100,000? And I was genuinely positively optimistic about the outlook that everyone had, that there was so much interest in that, and the desire to be able to say, oh well, how can we jumpstart this? How can we take a little piece of this and do a portion of it? And we love to be able to do that in sustainability because we have a pilot project, we can show that it is provable, and then we can scale up from there.
Yeah, absolutely. So anyone who has connections to nonprofits who want to get invested in supporting the city and those plans, come talk to Sarah at the end. Any other questions at the moment? I have one more note card I got, which just says there's extra food for the taking. So on your way out, feel free to grab some extra food. Thanks, Michelle. I'm assuming that one's from you.
I have one for Austin. What about floors? We had a big shell construction thing, concrete, in like 60s, 70s, right? And beautiful forms, super efficient. I love shell construction. But we always need floors to be flat, right? And we even like floors to be heavy for soundproofing sometimes. And I always felt like that thing in the 60s, 70s kind of phased out because, well, one, we just kind of got dumb and lazy, like to your point. But two was, well, it became hard to build they were amazing roofs and ceilings and difficult floors. Yeah. Like, where is that at, like, as we need to go higher, more stories, maybe not 30, but 5, what's the thought on really efficient shapes and structures? I mean, you showed that bridge.
I mean, that one, yeah, the bridge and then that floor system that you saw being dropped in. I mean, I don't understand the sound transmission enough to talk about it in an educated way, but he talks about, addresses it specifically and says they're actually really, sound deficient or something like that, where he actually addresses that even with the thinness of the material and something because of the geometries and the way it bounces off. And then what was the other question you asked? Of just it's flat, and that's where he's got all those ribs in there that actually flattens it out superficially while still saving 90%, 70% concrete.
That problem with the arches and stuff. It was like, well, you fill it with concrete then or something.
And it gets really heavy,
Yeah.
And the reason you said it's better to be heavy, I mean, the towers in 9/11, they actually collapsed because the floor system started pancaking on each other once it melted up there, and the weight of it, and I don't know enough to say, they wouldn't have collapsed with the different type of floor system.
There's an especially light building too.
Oh, comparatively, yeah. But I mean, these floor systems actually, and you can actually save a lot more on the foundation and other structural elements
it's a
too.
Huge argument for CLT and stuff is just like, hey, look, the foundation because wood's so much lighter.
And talk about local materials. You can literally make bricks anywhere, basically.
Awesome. All right, well, in lieu of any other questions, you can come up and ask us questions afterwards. The slideshow will be available after the presentation shortly. You can pick up some more food on the way out, and it's great to see you all today. Thanks for coming out.